A quick introduction to Julia sets, Part 3. Here's a definition. The filled Julia set for a function f sub c of z equals z squared plus c is the set k sub c of all points whose orbits do not diverge to infinity. For the function f sub c of z equals z squared that we've just been looking at, the filled Julia set k sub c is the set of all points either on or inside the unit circle. The boundary of the filled Julia set k sub c is what we call the Julia set of f sub c, and we label the Julia set as j sub c. For the function z squared, then, the Julia set j sub c is the unit circle itself. For any c, the Julia set is where the chaotic behavior is. On one side of a Julia set, all the points' orbits escape to infinity. On the other side, all points are attracted to an attracting cycle if there is one. When there is no attracting cycle, there are lots of other things that can happen. Let's let c equal the complex number shown here. So now our function f sub c equals z squared plus c involves both multiplication and addition. Let's plot some orbits and see what happens. Here's a quick reminder of how that function behaved. It took horizontal lines to what looked like parabolas that opened to the right. And it also took vertical lines to what seemed to be parabolas that opened to the left. It also took circles to what looked like circles, or at least they're some kind of loops. And sometimes those loops were traced out once, and sometimes they were traced out twice. Let's have a look at the 8th iterate of the function. Look at that. It looks like there's a fixed point right around there somewhere. And swinging back this way. And that, we see some points seem to escape to infinity and others get stuck in some kind of a triangular pattern. And look at the origin is on the point of one of those triangles. And again, as we zip around in the plane, it looks like some points are being trapped in some kind of a triangle and others have escaped to infinity. And how can we tell which points on the plane are going to do which? It would be useful to have a picture of the plane divided into two colors. One color for those points whose orbits seem to be bounded and trapped in a triangular pattern, and the other color used to distinguish points whose orbits have escaped to infinity. That's the purpose of our Stage 1 program. For each point z on the screen, the program calculates enough members of the orbit of z to decide if the orbit of z stays bounded or not. That is, whether it's in the filled Julia set or not. If the orbit remains bounded after we calculate some maximum number maxits of iterations, we'll color the point z some nice color like slate blue. And if the orbit escapes in less than maxits of iterations, z will be colored lime green. The actual test will be this. Is the iterate more than 2 units from the origin? It can be shown that if the modulus of the kth iterate of z is greater than 2 for some k, then the orbit of z diverges to infinity. Let's plot some orbits and see how we did. Sure enough, as long as we stay in this green area, the orbit of the point goes off to infinity, escapes to infinity. Even when we come down here where it's getting kind of tight between the green and the blue area. But nonetheless, no matter where we pick a point, if it's in the green region, its orbit seems to escape to infinity. Now let's go inside the blue area, where sure enough the orbits are bounded for all the points that we're checking anyways. So this blue area must be the filled Julia set. The boundary that you visualize separating the blue and the green regions is the actual Julia set itself. Look at that. There's 0. It appears to be on an attracting 3 cycle. And way down there where those things all meet, there seems to be a fixed point, a repelling fixed point at that. So there are lots of features to discover about this picture.